Science, Oliver.
Okay, it's a relief that tentative glitches in these lectures won't find their way into the feedback form anymore. I hope everybody copy pasted that link. I will write it out soon. But before, let me remind you of the bottom line of the last lecture. This is the endpoint three-level amplitude of the open superstring, the RMS formalism. The integrand is essentially a correlator of n-vertex operators. But there is a certain redundancy that you need to mod out by. What you already saw in case of the bosonic string, there is Möbius transformations on the punctures that allow you to put any triplet of punctures to 0, 1, and infinity. And there's a Jacobian up here to really implement this modding out properly. And for the superstring, there's a second kind of redundancy. It is, if you wish, the fermionic friend of SL2. So there, it's a little bit more subtle. You have two flavors of vertex operators, the -1 and 0 picture that you saw before. And modding out by fermionic redundancies, this amounts to putting any two vertex operators into the -1 picture, the other one's the 0 picture, and make sure that we take this compensating factor along. Because with this one, then your amplitude is independent on which pair of vertex operators you have sent to the -1 picture. So this is a lot of consequences of superconformal field theory miracles that you see in action here. So even though we make a lot of manual choices, the result computed by that formula is independent on which punctures or which external states you use to fix the redundancies. Okay, so let's apply this at the 3-point level, and I'm going to put your attention to the comparison to the bosonic string. I'll try to convince you that supersymmetry is your friend, that in spite of these extra fields, psi, on the world sheet, the result becomes simpler if you combine all the contributions. Okay, so let's see what I might mean by that by computing the 3-point instance of that general formula. So, as before in the bosonic string case, 3-point correlators of conformal primaries will be completely independent on the punctures. So this will be a consistency check, that everything is going well with our Wick contractions. And I will just follow the choice advertised here on how to fix the punctures and how to oh no, here in particular, I will use the ghost picture assignment that the second and the third leg will enter the -1 ghost picture. So for the first leg, we still take the 0 picture vertex operator, which was the slightly longer expression. And then for the other two legs, the second and the third, we use the -1 super ghost picture. These are the slightly shorter vertex operators. Okay, that's our task to compute. Fortunately, this correlator will factorize into a psi contribution and into an x contribution. There are no mutual OPEs between the psi and the x field. So that's the first piece of good news. And now, second piece of good news. The exercise of OPE contracting that guided exponential, we already did that exercise for the bosonic string. So there's nothing new happening here. So let's start with the contribution of the dx. We looked at this with respect to the SL2 behavior. We saw that if you use transversality of the polarization vector, epsilon of k equals to 0, then you can really eliminate the third momentum and get the right kind of z-dependence. Okay, and once you pick the dx term here, then you will have a psi-psi contraction over there, which will introduce epsilon 2 to epsilon 3. Okay, so this is all the contribution from the first term. And now here the second half of the zero picture vertex operator. This will hand you a 4-point function of the psi field, and you just work yourself through the possible Wick contractions. And let's also note that this is normal order, so you don't pick a pole from contracting this against that. They don't contract. Okay, and then the psi part gives you something like this. And up to momentum conservation and transversality, this is just once more the 3-point vertex of Young-Mills. Okay, here for external bosons, it doesn't matter whether I speak of pure Young-Mills or super Young-Mills. You probably heard this. Yeah, so we are lucky that we are getting the expected low energy behavior, but now there's no alpha prime correction. Remember, the bosonic string calculation, there was an extra term, plus 2 alpha prime times, yeah, something with 3 momenta. But this one doesn't occur here, in case of the superstring. So this is the reward for including the psi-psi part into the vertex operator. It's the joint effort of the worldsheet bosons and worldsheet fermions that kill a lot of extra burden in the superstring. So in particular, it's in the end the effort of worldsheet SUSY that we have no superstring counterpart of the F-cube interaction that we saw in the bosonic string. By the way, this F-cube is incompatible with space-time supersymmetry. It would be pretty weird if we had this one in a space-time supersymmetric superstring. Though we didn't have a chance yet to see why the superstring is space-time supersymmetric. All this to say, it's really necessary that we find the dropout of F-cube.
Can you repeat why the alpha prime bit drops out?
I'm sorry?
Can you repeat why the alpha prime drops out?
This is hidden in the twiddle here. I'm not tracking the overall factors here. I will be more careful in the closed string section. I'm sorry?
Could you just repeat why the relative one drops out?
Oh yeah, right. Here the OPEs of this one with the exponential introduce one factor of alpha prime for each one.
Okay.
Maybe I should have said alpha prime to a half. I'm sorry. Okay, and as far as higher multiplicity examples are concerned, here this is again outsourced to an exercise. One of the most illuminating tensor structures is this one, the same guy that I asked you to focus on in case of the bosonic string 4-point function. And it also uses specific combination of the superghost charges, which is somewhat tailored to the tensor structure. So this example here gives you the maximum insight on how the superstring compares to the bosonic string. So it's a really rewarding thing to go through the coefficient of these tensor structures, both in the bosonic string and in the superstring, and to compare. So what you should find is that the alpha prime to 0 limit, you get the same result, regardless on whether you do it in the bosonic string or whether you do it in the superstring. I mean, both of these theories have in common that at alpha prime to 0, you should recover Young-Mills as the low energy limit. But in the bosonic string case, we saw this tachyon pole. It doesn't contribute to the alpha prime to 0 limit, but yeah, you should also see that there is no tachyon pole here in the superstring calculation. And you should also see, when you're really careful, that this lines up with the claim that I dropped in the Tuesday lecture, that if you go through all the possible tensor structures, you can peel off the color-ordered tree-level amplitude of Young-Mills from the 4-point function of the superstring. Note that this is really tied to being the superstring, because in case of the bosonic string, there would be some pollution with more appearances of alpha prime. But of course, there is this integral that we discussed from various perspectives on Tuesday, and which is a particularly nice one. It has, for instance, uniform transcendentality. That's something I try to elaborate on in the afternoon.
Sorry, can you explain a little bit, because the alpha is proportional to the tension of the string, right? So
The inverse tension.
the inverse.
Yeah.
So what it means to have an infinite tension for the string?
Oh yeah, right. If the string has infinite tension, it doesn't like to wobble. You need to work hard to excite it. And the higher the mass of the excitation, the more difficult it is to really get this excitation to exist. And here for the massless states, it's still okay at infinite tension. But you won't manage to produce the heavy vibration mode at infinite tension. Okay, there's the opposite regime, quote-unquote alpha prime to infinity, where the strings become tensionless. Then they like to wobble around in all kinds of ways. And this is where, schematically speaking, all the higher spin excitations become massless. But it's, of course, highly delicate to do massless limits of higher spin. Yeah, maybe you can take a photo of this exercise if you didn't copy it so far, because I'll erase some stuff. So the next topic is the closed string. You might wonder about the time planning of this lecture, that I spent so many minutes on open strings. When will I ever get to discussing the closed string? The good news will be most of the hard work is already done if we have the open string under control. So most of what I will say about the closed string is about recycling, how to rearrange open string results in a way that you get a closed string for free. This will be the mindset for the next section. Okay, as you can imagine, the first part is to write down vertex operators. And this can directly be used to formulate the amplitude prescription. And at the level of vertex operators, we are in really good shape. The closed string vertex operators effectively factorize. So what I mean by that is, if you wonder how to insert a closed string state in a worksheet, what you can take is a product of open string vertex operators. Here I'm already cutting it down to the massless level, to the massless bosons. And you take one open string vertex operator that mostly depends on Z, and then something that smells like its complex conjugate, which mostly depends on Z bar. Okay, so this we can do for both the bosonic string and for the superstring, but let's directly jump to the superstring case, where we need to keep track of the superghost charges. So I can make some independent choices of whether I use the 0 picture or the -1 picture for the respective open superstring halves. So I need two ghost charges, two chiral halves of the superghost charges, Q and Q bar, to characterize the closed string vertex operator. Now, I was trying to be careful about where to put the bar. So here this epsilon bar, it's not literally a complex conjugate, but you may choose it independent on the epsilon from over there. So it's really about doubling the degrees of freedom. But the only thing you need to make sure is this epsilon bar should still be transversal. So here, what you want to construct is a conformal primary of weight 1, 1, with respect to both the holomorphic and the anti-holomorphic stress tensor. Okay, so here there's this warning that the epsilons can be independent on the two sides, but the momentum in turn must be the same. So here, this is the related to the word effectively. This factorization may look a bit weird with respect to the plane waves. There's always an e to the ikx. It's a bit weird to split the plane waves here. That's why I'm saying effectively. But if you really work with having a plane wave in both factors, it works as a cooking recipe. It will give you the correct results. So for the purpose of getting the closed string amplitudes done, they do factorize. Okay, maybe I should give you the more intuitive version of what I just said. Well, the quest for vertex operators that are compatible with superconformal symmetry, this is just about getting the spectrum. And by saying that the vertex operators factorize, this is tantamount to saying that the spectrum has double copy form. So the viable vertex operators are just scanning what kind of excitations can I put on a closed string. And as a nice feature of the closed string, you can independently send left and right moving vibrations through it. This is about the independent solutions to the wave equation. And let's contrast this with the excitations you can put on an open string. I didn't really elaborate on that, but whenever you play with open strings, you're supposed to put boundary conditions on the endpoints. And these boundary conditions, they will tell you precisely how their excitations reflect. So I can only put one independent excitation here, and I can't put a right mover on the same open string. But instead, if I take the tensor product of two open string states, I do arrive at the same degrees of freedom as found here in the closed string with independent left and right movers. Okay, so morally, this first guy takes care of the left movers, and the second part takes care of the right movers. And this factorizing structure is, in intuitive terms, saying that they don't interfere at the level of the spectrum. But, okay, now the hard part is to uplift this statement to the interactions. And this is what we will spend most of this lecture on. But maybe I should elaborate a little bit more on the kind of master states that we generate in this factorizing prescription for vertex operators. Okay, I was ignoring the fermions in the open string case, so accordingly there are a lot of states in the closed string spectrum which I won't discuss here. But let's just see what we get out of this tensor product of an epsilon and an epsilon bar. So let's decompose this with respect to the Lorentz group. And as I said, we just do it for the outer product of open string bosons. So as you can anticipate from this vertex operator, the amplitudes will be multilinear epsilon and epsilon bar. For each external state, there's an epsilon and epsilon bar. And this will produce the polarizations of several closed string states. So here is some elementary representation theory of the Lorentz group. If you take a bivector, then it has three Lorentz irreducibles, the symmetric traceless part, the antisymmetric part, and the trace. Okay, I guess most of you have seen this and will be a bit bored, but just to have everyone on the same page, here this symmetric traceless part. This is spin 2 in terms of Lorentz representation theory, and it furthermore inherits the gauge redundancy that we found for the gluons before. And whenever you have a massless spin 2 field with a gauge redundancy that will now have a vector index, then this is necessarily gravity. So this is necessarily diffeomorphism invariance, I should have said, and gravity is the unique diffeomorphism invariant theory of massless spin 2. So there's no escape from saying that this is the graviton. Okay, and the remaining Lorentz irreducibles that you get for free in this tensor product, yeah, this is just the B field and the dilaton. Maybe a small technical side remark. It's not as simple as using the Minkowski metric in D dimensions here. You must make sure that you take the trace in a way that transversality is preserved. So, strictly speaking, this is the metric with respect to the little group SOD minus 2. So be careful when you insert dilatons. But yeah, good news is we will work out some double copies of open string polarizations, and you automatically have the direct sum of all graviton amplitudes, of all graviton B field mixtures, and so on. You can't help computing all of them at the same time. And of course, you're free to truncate to your favorite choice for the external states. You can always filter on the graviton, for instance. Okay, now for the correlation functions of these vertex operators here, let me be clear about all the convenience that you will find. So here, this vertical bar up there means it's more or less the same expression as seen for the open string, but you put a couple of vertical bars on the worldsheet fields. So in the open string section, we were only seeing the holomorphic derivative, and we were seeing one of the species of worldsheet fermions, psi. But there was also a psi bar in the worldsheet action. And of course, you can also take the anti-holomorphic derivative of S. So these are the guys that you will find in the right chiral half. So this is, if you wish, the definition of this guy here. Yeah, the good news, since you are coherently replacing these guys when you go to the second chiral half of the closed string, a lot of big contractions are absent. At least at genus 0. At genus, higher genus, it depends on how you deal with the zero mode, whether they still factorize or not. But if you're willing to carry around loop momenta, then they factorize at any genus. I mean, then the cross contractions are absent at any genus. And of course, the big contractions of these guys, you get it from the big contractions you already did by putting complex conjugates, Z bars everywhere. Yeah, so from this pattern of big contractions, we can safely say that when it comes to computing closed string tree amplitudes, the integrands will factorize. So now it's time to write down the amplitude prescription. So this is now for the type 2 theory. These are the two possibilities to get a closed superstring theory without tachyons. There's a type 2a, type 2b, which you can only distinguish once the fermionic sector of the open string is spelled out. So let's just collectively say type 2 for the closed string amplitudes you will see here. Okay, and let's now be a bit more careful about the alpha primes.
Is there a reason why it changes from A to M now?
Oh yeah, M I usually use for color dressed amplitudes for open strings and A for color stripped. Now closed string states don't have any Chan pattern factors, no color degrees of freedom, so there is no color strip object we might look at. That's why I'm using M. And of course it's useful to have a different letter for open and closed string amplitudes because they will appear in the same formula later on. Yeah, thanks a lot for raising this point. Okay, and I was continuously saying that more or less everything factorizes that you have seen before. In particular, the way how you fix the modular factorizes. You can fix both the Z and Z bar punctures. You put 3 punctures to 0, 1, and infinity, and this will impact both the B and the B bar side. It's almost a triviality. And the story with the superghost pictures, you make independent choices in the left and right moving sector to put 2 of the Q's to be -1 and also 2 of the Q bars to be -1. So all of this I squeeze into the notation, take the absolute value square of the formal inverse volume. Okay, now we are supposed to insert integrated vertex operators. In the open string case, the integrated vertex operator was inserted on the boundary and integrated over a certain segment of the worldsheet boundary. Now we are in a different topology. Now we are talking about closed string worldsheets, which at genus 0 have the topology of a sphere. So this time there is no notion of being neighbors to each other. You independently integrate all the punctures over the entire sphere, which you can parameterize through C plus a point at infinity. So it's C to the n as an integration domain because there are n punctures. And now here come the correlation functions from the open superstring. And here is the factorization that I kept on advertising. Given that there are no mutual cross contractions between the fields with the bar and the fields without the bar, this is really about computing independent correlation functions. Okay, we for instance just computed the 3-point function for the open string, then we just square the underlying correlator. But at the 3-point level, the correlator is already the final answer. There are no integrals for 3 points. So we can immediately say that the 3-point instance here is a product. Okay, maybe I should insert a new headline before making this factorization statement of the 3-point functions. The purpose of the next section is to investigate, well, if the spectrum factorizes for the closed string, to which extent can we also see a factorizing structure in tree-level amplitudes? And the only kind of couplings between left and right movers appears through the integrals here. So it remains to check to which extent we can factorize these two-dimensional complex integrals, these complex integrals with 2 real degrees of freedom, to which extent we can factorize them into open string-like integrations. And this goes back to monumental work from the 80s by Kawai, Levin, and Tai. So I'm about to tell you about the KLT relations from 86. Yeah, and this question I just brought up has a positive answer. There is a way of effectively factorizing these integrations here. You can factorize the integrals modulo phases. So the KLT relations that you will see in full glory later on, they have a schematic structure. If you're asked to do a complicated complex integral, you can reduce that to simpler integrals of dz and dz bar, where you just integrate over a slice of real axis. But this disentanglement goes on the expense of introducing some complex phases. So these complex phases will amusingly depend on the Mandelstam invariants. Remember, these are the dimensionless guys where alpha prime is going with k dot k to make this a valid exponent.
So in the open superstring, some operators, yes, were the -1 and some were the 0 ones, whereas here we seem to just have the 0 there.
Oh yeah, right. So this is something I absorbed into the notation a few blackboards ago.
Okay.
Thanks a lot for bringing this up. So this inverse super SL2 volume is understood to lower two ghost pictures here. Yeah. So before fixing any fermionic moduli, they're on the 0 picture, but then two of them drop down to the -1 picture by virtue of this. Yeah, thanks a lot.
And also reinstated alpha prime.
Okay, so this will make sense in maybe 30 minutes. So far it's a convention. I was promising the last lecture to be more careful about alpha primes. Okay, so let's look at this claim in more detail, this factorization modulo phases. There is no integral to do at 3 points, so there's also no chance to see any phase at 3 points. So all the 3-point closed string amplitudes in type 2 are on the nose the products of color-ordered superstring trees. Here. And these 3-point superstring trees, in turn, we just worked them out, they are identical to the Young-Mills 3-point amplitudes. So here, this full-fledged 3-point string amplitude, it boils down to a product of field theory quantities that have no alpha prime whatsoever. There is no alpha prime dependence to the 3-point amplitude of the type 2 superstring. But if I were to look at the corresponding bosonic string amplitude, then there would be these F-cube additions here in the open bosonic strings, and then you can follow how they square these F-cube contributions. But at the superstring level, it's all independent on alpha prime 3 points. Yes, please?
There is a question that I would expect to compute some amplitude between some of the physical space, let's say a graviton or a big field, but it seems to be hidden in interpretation, right? So what kind of free amplitude are you computing?
Okay, very good question. So this factorization claim, it applies to the functions of epsilon and epsilon bar. And at this point, you don't commit to which of the specific closed string states you want to look at. At first, you compute this kind of meta object that depends on n epsilons and n epsilon bars. And once you're done in simplifying that, then at the last step, I would suggest you to plug in your favorite polarization choices. So in particular, the dilaton will contract left and right numbers. But it's only a pain if you insert this too early on. Be patient with applying that rule. Any further question? Okay, so 3-point wise, there's not much to be done about disentangling integrals. But now at 4 points, this is the first non-trivial instance where we need to work on the integrations. So first of all, let me present it as a claim. And this is the result of the Kawaida-Type from the 80s. The claim is, if you're after the 4-point function of the tattoo superstring, then you can get there by squaring color-ordered 4-point function of the open superstring. But now, there is some more stuff. Here, this will be the first instance of this, these phases. And the precise arrangement of these phases, it goes like a sine function of pi s12. So the sine function is just the antisymmetric combination of the positive phase and the negative phase. Yeah, so here the idea is, suppose you already have the open string 4-point functions in your pocket, just recycle them, throw them into a KLT, this KLT formula, and make sure that you decorate it with this sine function. Okay, so this sounds really like a luxury. So let me try to give you an idea of how such a claim can be proved. And to already say it in advance, this proof is essentially a piece of complex analysis. And the main actor in this piece of complex analysis is the Kober-Nielsen factor. Remember, already the open string gives you these contributions with all the absolute values raised to some power. And of course, if we have 2 copies of Kober-Nielsen, then there's a different exponent here. Yeah, so it is this Kober-Nielsen factor here that will drive the complex analysis that we are about to do. Okay, time to lift the secret on the other backboard. Yeah, I guess here it's a delicate task to find a balance between how much details to spell out and how much time to save for other topics. So, to some extent, I would ask you to consult the paper to read about the proof of Kawaida-Type. But at least I want to give you a flavor of what's going on and what the shape of this complex analysis is. Okay, so the proof has essentially 5 steps. And we should definitely make sure that we fix our SR2 frame early on, such that the only integral is about Z2. And quite naively, we can decompose our integration variable into a real and imaginary part. So in the first place, the integral d square Z2 is an integral over the real part, the x, and an integral over the imaginary part, dy. And note in particular, as a function of x and y, the integrand is actually analytic. Okay, in the first place, x and y are real, but let's now promote x and y to be potentially complex. Then we are looking at analytic functions in x and y. So in particular, you can contemplate a deformation of the integration contour for x or y. So the original integration contour is integrate y over r. For sure, it's the imaginary part of z. It should better be real. But when thinking about the integrand as an analytic function of y, why not play with this contour and go to imaginary values of y? Okay, sounds good, but we must be careful about the details of this analytic function, y. This Kober-Nielsen factor, it actually introduces some branch points in the y plane. I mean, there are branch points whenever you insert 0 here for the differences of the z's. So there are a few values of y where some of them here vanish. So this is a branch point, and this is a kind of obstacle in doing contour deformations. So more specifically, here in this 4-point context in the above frame, the branch points occur at y equal plus minus ix, or y equal plus minus I1 minus x. Quite simple. Plug in these branch points into here, and then you are at the vanishing locus of these Kober-Nielsen constituents. So these are the dangerous points. And for sure, whenever we do contour deformations, we must not cross any branch points. Now, here on the upper blackboard, here the leftmost panel, you will see the contour deformation that we can afford to do. We start with the red contour, where y is on the real axis. But then we want to promote it to be purely imaginary, and this almost works. If you were to choose y to be purely imaginary, then you would be crossing the branch points. So these branch points are marked on the imaginary axis, these 4 bullets, plus minus ix and plus minus I1 minus x. So these 4 branch points you mustn't cross. So the best you can do is, you can choose y to be almost on IR, but you must maintain a small real part. You must stay an epsilon off the imaginary axis. So here this plus minus epsilon with real epsilon, this stems from evading the branch points. Okay, so we will take this blue integration contour henceforth for y. Now let's see how this plays out with the target integral which we actually want to compute. Oops. So if you are on the way to getting the 4-point function, of course there is a lot of polarization dependence from the correlators. There's a lot of stuff which doesn't really matter for doing the integral. So I'll be pretty sloppy in writing this proportionality twiddle. I'm ignoring all the polarizations. But what I can't ignore is the contribution of the Kober-Nielsen factor, because this is the one that sets the branch points. Yeah. So this is the essential challenge here of this piece of complex analysis. And it doesn't even matter if there are some integer offsets for the exponents of Z2 and Z2 bar, because these integer offsets won't alter the monodromies. So that's why I'm not caring which specific contribution of the correlator we look at. Okay, so let's now apply that contour deformation to Z2 and Z2 bar. If y is almost imaginary, then both Z2 and Z2 bar become almost purely real. So we are almost there in doing real integrations over Z2 and Z2 bar. I mean, this is the point of rotating the integration contour for y, to avoid having to integrate away from the real axis. We know how to integrate on the real axis from the open string, and we want to transfer that knowledge to the closed string. That's why we like integrals in the real axis. But okay, now what goes on with the covariance factor? So in the original contour, the absolute value, or ZZ bar, was positive definite. Yeah? ZZ bar, of course, it should be positive definite if Z bar is the complex conjugate of Z. But now we have independent integrals over Z and Z bar. Now they are no longer complex conjugate of each other. So now ZZ bar may become negative in certain segments of this integration domain. So I have converted a positive definite quantity into some, well, partially negative quantity. That's not correct. There are some phases. Whenever ZZ bar is negative, then there's a phase of the first time, and whenever 1 minus Z times 1 minus Z bar is negative, then it's the second type of phase. Okay, and in principle there are 9 different cases to determine these phases. Instead of going through all the 9, let's focus on those that actually contribute. So setting these contributions is done in the right panel of that figure. Let's fix Z, and let's look at the contour in the Z bar plane. So there are 3 cases how this might happen. So if we fix Z to be smaller than 0, then the Z bar plane is looking roughly like that. Remember, there's a slight displacement of y. Y is not exactly on the imaginary axis, but it's off by an epsilon. And the same off by an epsilon propagates here. The Z bar is slightly below the real axis. So if Z is smaller than 0, then the Z bar contour goes like this. And again, we can do more contour deformations as long as we stay away from the branch points. So we should stay away from the branch points at 0 and 1. And now we can close the contour at negative I infinity. So here, this contour, the Z bar plane, it can in fact be contractible to a point. So by Cauchy's theorem, that integrates to 0 when regarding this as an analytic function in Z bar. And almost the same statements go through when Z is larger than 1. In that case, the displacements from here translates into the displacement shown here, that the Z bar is slightly above the real axis. So you're walking around the branch points in a slightly positive manner. So this time, you can close the contour at plus I infinity, and it's again contractible. So also there, what you get is 0. Isn't this nice? For substantial parts of the Z integration domain, we get 0 upon integration over Z bar. And the only situation where this is not possible is when Z bar is in between 0 and 1. So in that slightly more awkward setting, the contour in the Z bar plane is displaced in a, well, irregular manner. We start being above the real axis, and then we dive below it. And this is the only case where you can't close the contour at infinity. This is where you can't contract the integration contour to a point. So this is the only place where you get stuck on the Z2 integral. But I don't mean getting stuck in the sense of we can't do it, it's just that it doesn't integrate to 0. And this is what we have to hand to the next step in our proof of K of T. Oops, so this is now the 4th step in deriving KLT. So we've just seen that the only contribution arises from values of z that are between 0 and 1. So we are specializing the first integration contour to between 0 and 1. And at fixed choice of z, we can again do contour deformations in the z-bar plane. So we can't close the contour at infinity, but we can do something slightly weaker. Here in the z-bar plane, we can wrap the right half of the contour around the left part. No, sorry, this is hard to describe in words. Let me draw it first. Okay. So the upper branch here is the same that you already saw in the figure. We start from minus infinity and we are slightly above the real axis. Let's call it C minus. But now here in the original contour, you were going off to positive real parts, but you dive below the real axis. So you grab this right half and wrap it around the origin. And here, this is a legal contour deformation because we didn't cross any branch point. We didn't cross the branch point at 1, and we also didn't cross the branch point at 0. So actually, it's only because of that branch point that the integral is non-zero. Otherwise, we would pull it off to infinity over here. Okay, now there's an important phase that will enter the game. I was already warning you before. After these contour manipulations, z and z bar are not complex conjugate of each other. So this product here is not positive definite. However, the original integrand we were looking at, the original integrand had something positive definite. This was our starting point. So we have cheated by a phase. We have cheated by a phase, the integrand. So now I am spelling out the specific phase difference when you walk on the blue contour. And importantly, depending on whether you're above or below the real axis, you have a different phase. I mean, effectively, you are doing a big circle around the branch point. You're getting a phase difference of 2 pi I s. So we must have opposite phases on the C upstairs and the C downstairs. Okay, so now let's finish the job. Oh, maybe I should have left this. So by taking all of these steps together, what's the behavior of this integral here? So first of all, for the z integral, we have seen that all the contributions come between 0 and 1. That's the selection rule up there. And now for z bar, maybe I'll first spell out the covariance factor for z. But now, as far as z bar is concerned, we are integrating over this blue contour. And there are different phases associated with these subcontours called C plus and C minus. And note that these arrows are in opposite directions, so they have a relative minus sign due to the relative orientation. All this to say that contour here for Z bar, you can wrap it up to be the integral from -infinity to 0 dz bar. And yeah, the phases come with a negative sign. Okay, so now when the dust settles, you can identify a sign function of S12. So what we get is, maybe I'll write it down in that last line. We first of all get an open string amplitude tailored to this ordering, and integrating Z2 from 0 to 1 is nothing but the color ordering 1, 2, 3, 4. So we are reading this off from integration domain on Z. And here this contribution to the second line, since we are integrating Z bar from -infinity to 0, this corresponds to a color ordering of 2, 1, 3, 4. So this is what we read off from that. Okay, and this is indeed the claim that I've erased a couple of minutes ago from here. This finishes the proof of the Cavallo-Venn tie relations at 4 points. After patient complex analysis and keeping track of all the phases, we are arriving at this factorization modulo phases that combine to be a trigonometric function of the Mandelstam invariant. Okay, this was admittedly quite technical. Sorry in case I lost some of you, but even if you didn't follow in the last 15 minutes, this is now a good moment to join in again. I will now proceed to applying the formula. If you're willing to just trust it without a proof, then you'll be immediately in business. Yeah, we already found a nice expression for the 4-point open superstring tree. Let's just insert these 4-point results. I'm quoting now the gamma functions that we found for the alpha prime dependence in the Tuesday lecture. So there's the sign function from the KRT formula, and now for the first superstring tree, I use the Young-Mills tree times the following gamma functions. And now from the second super Young-Mills tree, from the second open superstring I will have, we will just get super Young-Mills in a different color ordering times more gamma functions.
Actually, only this is a typo because yes, the A bar is different.
Okay, I used the reflection identity. Okay. Yeah, that's good. Yeah, you get a positive sign if you reverse the ordering. Yeah. I'm already trimming it into the form that endpoints can be formulated more smoothly. Sorry. Okay, now there is a funny formula relating the sign to inverse gamma functions. By putting together the trigonometry with the gamma functions you see, then you can bring all the alpha prime dependents in this very symmetric form. So this is both the sine and the gamma functions that you see in the previous step. Okay, and without even computing the prefactor of it, let us note that this combination of gamma functions has the following low energy behavior. If I Taylor expand an alpha prime, if I probe the field theory limit and the first alpha prime corrections, then this is 1 minus 2 zeta 3 S12, S13, S23 plus order alpha prime to the fifth. Yeah, just some elementary results of the Taylor expansion of the gamma function. So in the field theory limit, this is supposed to give us type 2 supergravity, or say the unique spin 2 theory with diffeomorphism invariance. So whatever the coefficient is, to get a consistent field theory limit, the coefficient must be the supergravity tree. By demanding a consistent field theory limit. Okay, and so far we haven't evaluated the precise coefficient. If you now go carefully through the above formula, then you find the following representation of the supergravity 4.3. You will find that you can assemble it from Yang-Mills. There is one super Yang-Mills tree in the 1, 2, 3, 4 ordering. And there's another super Yang-Mills tree in a slightly different ordering. Yeah, and there's this momentum factor here that stems from the sine function when you rearrange it in terms of gamma functions. It's probably rewarding if you go through the details at home. Okay, now this is the first, or maybe the second instance of a double copy formula for gravity trees. We saw it in the 3-point case already, where the factorization was somewhat trivial. But also here at the 4-point level, we see that as a shadow of these Contra deformations in alpha prime to 0, we managed to express a supergravity tree amplitude in terms of a square or bilinear in different color-ordered Yang-Mills trees. And now we need to be careful what kind of momentum dependence is induced by this Contra deformation business. So this is, if you wish, the KOT formula for field theory, for supergravity. But it's maybe even simpler to write down the full alpha prime dressed KOT formula. I mean, this factorization statement goes through for all the alpha prime corrections, and you can deduce this alpha prime dependence here from open string input. Okay, so it was a lot of words about the factor of 1 here, but of course there's now this infinite tower of alpha prime corrections, and here the first one will compensate for all the kinematic poles inside the supergravity 4-point tree. This has poles in all the ST and U channel, but after multiplying by ST and U, all the poles are gone. This must be a local contact interaction. So this is now the closed string counterpart of the F to the 4th interaction that I showed you in the first lecture. From this specific alpha prime correction, we can infer that the effective action of type 2 superstrings contains the effective operator alpha prime q zeta 3 r to the 4th. Okay, so R refers to the Riemann tensor, or more precisely to the Weyl tensor, and it's running a similar argument as before. We have 6 more derivatives in that term as compared to the field theory limit. Now the field theory limit comes from an Einstein-Hilbert action. How can we sprinkle 6 derivatives into Einstein-Hilbert while maintaining a local structure of a 4-point contact interaction? So by just counting mass dimensions, you must have 8 derivatives in here from this, in this R to the 4th. And these 8 derivatives, they must come in a diffeomorphism invariant manner. So that's why you don't see a derivative of the gravitable field, but instead it's this full nonlinear expression for the Riemann curvature to really have a diffeomorphism invariant way to assemble these derivatives. And with similar arguments, you can go through all these higher order contributions and identify some d to the 4, r to the 4th, and so on. So this is another example of how the alpha prime expansion of string amplitudes allow you to assemble the effective action contributions. But of course, this is all about the tree-level effective action, and you still have to work to get the one-loop contribution to r to the 4th. Combining the two will be an interesting showcase of S duality. But yeah, I regret this will be beyond the scope of this lecture. Good. The next step is to just state the endpoint version of the KLT formula. But how are we doing on time?
Kind of at the end.
So shall we relegate the endpoint version to the afternoon?
Yeah, maybe it's most important to ask the questions now and then.
So your gamma function matches there, the spin is too close to theta functions. Did you cancel out a factor in the numerator?
I hope I did.
Can you repeat the question again?
Your gamma function factors, they look very close to theta functions, but not quite. The denominator has dropped an integer. No, first.
So what I'm inserting is the sine function is this one. And I furthermore use momentum conservation that s plus t plus u equals 0. Yeah, let me amplify a bit on that. It's quite nice to see the structure of the poles working out correctly. I mean, each open string tree has by itself an infinite number of poles. The first open string tree has poles in the S and the T channel, and the second open string tree has poles in the S and the U channel. So you may worry that you are overshooting in the S channel. There's a double pole for each mass level in the S channel if all you have is the product of open string trees. And the sine function is your salvation to cancel the double pole. There's a 0 coming at all the dangerous points. There's a 0 cancelling one of the two poles. So when all the dust settles, it's a single pole in the S channel. From the interplay of the 0 here and 2 poles from the open string house. And of course, a weaker version of all of that goes on in supergravity. If you look at Young-Mills, then there is S channel and T channel here. There is S channel and U channel there. So again, you might be worried about seeing a double pole in S12. And it's the job of this guy to cancel the double pole in S12. Yeah, so the pattern of momenta that you see floating around in the KLT formula, it's really a fine-tuned composition to make sure that the pole structure fits to Feynman diagram intuition.
Would you mind just either repeating or elaborating on the field theory argument that you assert that is the tree-level superactive?
Okay, right. So I was arguing before the closed string vertex operator contains a spin 2 part. And since it factorizes into open string chiral halves, it will inherit the linearized gauge invariance from the open superstring. Now imagine you do a gauge transformation on the left half, an epsilon to k, but you keep the right part inert as an epsilon bar. So there's really a vector-valued gauge transformation that you do that integrates to 0. But such a vector-valued gauge transformation, this is a linearized diffeomorphism. And don't worry that it's linearized. I mean, this is by construction. If all you do is play with vertex operators, you just see the linearized story. And only by resumming contributions at different multiplicities, only then you generate a nonlinear tail. So we are looking at a diffeomorphism invariant theory of massless spin 2. And this is always gravity. Okay, there's also some extra to this. as I was pointing out before, you're computing a bilinear in epsilon and epsilon bar. This is not only containing a 4 graviton amplitude, but also, say, a 4 dilaton amplitude, or all compositions of graviton, B-field, dilaton. But it's sufficient to demand that you're on the right field theory limit in the 4 graviton case. That the behavior of all the other components with B-fields and dilatons, they are a corollary.
Are there such KLT relations as Crayola, or just true?
Oh, okay, yeah, this is really a current edge topic in research. If you find a KLT formula at one loop, urgently write a paper about it. There is a cleanup version of KLT at tree level. I can at best allude to it in the afternoon. KLT gives you the closed string as a square of open strings. But there's a even nicer formula at the level of the alpha prime expansion. If you have a good filter on the multiple zeta values, then you can get the closed string as a projection of the open string. The projection is about killing zeta 2 and doubling zeta 3. It's called the single valued map. So at tree level, the end result is you don't even need KLT. The closed string can instead be written as a single valued open string. And I believe that this statement is way more robust to be carried over to higher genus. There's a lot of mathematical machinery behind the notion of single-valued integration, and you can see from these mathematical tricks that it's not confined to genus 0. It may be very, very hard to get an explicit form of such a single-valued projection to higher genus, but maybe this is more the practical kind of problem. So I believe that ultimately there's a lot of recycling also at loop level to get closed string data from open string calculations when looking at them from the right angle. Yeah, Douglas.
So yes, since this is definitely a very, very striking feature that gravity is like the square of Gates theory, and we went through very nicely the derivation. Yes, just to again recap, the essential characteristic is these Coban-Nielsen factors, and in particular how their phase changes in different parts of the integration contour. That's really the essential thing.
Okay, very good.
Bar to the S, and I see, okay, you, for the C minus contour, yes, which is above the axis, yes, so you have minus Z bar, okay, so Z bar has a positive imaginary part, so minus Z bar has a negative one, and this is... yes, you're right that G minus Z bar is negative, right?
Yeah, right, this is negative.
Okay.
But in our starting point, we were raising a positive number to the power of 2s. So to bridge from negative to positive, we will need to insert one or the other. Mm-hmm. And it's a convention choice of how you will set up the branch cuts. Mm-hmm. But once you have committed to one choice in the C minus contour, then the phase of the other one is a corollary, because you have a relative phase of 2 pi I, since you have walked around the origin by essentially a full circle. Mm-hmm. But yes, it's very good that you were...
Because this is really the essence, this is what survives and gives you, yes, something non-trivial in the end. Were it not for this factor, yes, one would get 0.
And this connects with one of the wisdoms in Claude's lecture. He was pointing out DIMREC is just about doing twisted de Rham cohomology. By doing DIMREC in Feynman integrals, you insert some epsilons into the exponents. Yeah? In Claude's lecture, he was having expressions of this form. And whenever you integrate stuff of that form, Claude was already saying, this is a matter of doing de Rham cohomology, but be prepared to see some multi-valuedness. Yeah? And the funny word, twisted de Rham cohomology, this is about keeping track of the multi-valuedness, keeping track of the phases that you will get when doing contour deformations as you would do it in conventional de Rham theory. So this is essentially about a theory of twisted cycles, which is an integration contour together with a branch choice. And this has been formalized in a piece of mathematics called intersection theory. And I think it was Sebastian Misera who firstly connected that with problems in physics. And it applies to both Cavallo-Bell and Tie and equally to Feynman integrals. It's the same mathematics that you use in QCD Pheno and in closed string amplitudes.
Okay. If you're the final question, you have more?
I'm good.
Okay, good. So then I think we can go for a lunch break, and we'll be back at 2.